Welcome. In this video I'll go through the energy principle and show how this is a way of calculating the stability of the plasma without having to know all the details about what the plasma is doing or the mode that's going unstable. It's a really efficient way, or leads to efficient ways of calculating whether a plasma is stable or unstable. And so the idea is we start from the normal mode equation, so with the force operator derived last time, and we show how this leads to the energy equation. So energy for the equation for the energy of the plasma, and particularly is the change in energy as the plasma is moved. So we start with some stationary equilibrium, and we give it some small change. So you give it a small push, and we ask, how does the plasma change respond to this small push? So if we move plasma a little bit, does it go back to where it was before and then oscillate, or does it keep moving and accelerate and then it becomes unstable? And the idea is that in ideal MHD the energy is conserved, and so any energy that comes out of the potential energy, for example, goes into the kinetic energy. And so if a plasma loses potential energy by moving in some way, then that energy goes into accelerating the plasma. And so because this energy is conserved, you can look at how the potential energy changes and how that and understand how that affects the stability. And this is kind of analogous to a ball on top of a hill. So if you think about, if you have a ball on top of a hill like this, you can balance it very carefully at the top, and it will sit there in force balance. But if you give it a very small push, so you give it some small displacement psi, it will just roll straight off the hill and this be unstable. Conversely, if your ball is sitting in a valley, it's like this. If you give it some small displacement psi, it will roll up the hill, then roll back down again, and the whole thing will just oscillate. And in the first case, this is unstable. So in ideal MHD, we expect omega squared is less than 0, so omega is imaginary. In this case, we'll get an oscillating solution, and this is stable, and omega squared is greater than 0, so omega is real. The case in between the two is called marginal. This is kind of like you have a flat surface. You make some displacement here. And this is the boundary between stable and unstable. This is marginal stability. And this is where omega squared is 0 in ideal MHD. And so what we want to do is work out a similar equations which determine, like a ball on a hill, when the plasma is stable and when it's unstable. And so the way to do this in the energy principle is to look at the potential energy. So the potential energy and in particular the change in potential energy as the with a small perturbation. An important point is, in order to be unstable, there only has to be one way for a plasma to move, to become unstable. And so if any psi can be found, so if there's any way that the plasma can move which will make the potential energy drop, and so i.e. go into this falling off a hill situation, and this change we call delta W is the change in potential energy. If that's less than 0 for any perturbation, then the plasma is unstable. And if you want the plasma to be stable, then all perturbations must lead to delta W bigger than 0. So now we can derive an equation for what delta W is. And so delta W depends on the perturbation psi. And the way we're going to do that is by using the normal force, the normal mode equation, which depends on gives the force as a function of psi. And this is the equation based for the momentum of the plasma. This is the force, this is the displacement, and we're now going to use this to work out the work done in moving the plasma. And so if when we push the plasma uphill, we'll have to do work on the plasma, and if we're rolling the plasma downhill, then the plasma will be doing work, and so that work will be going to the kinetic energy of the plasma. and so accelerate and become unstable. And so what we can do is do the force times distance. And that'll give us the work done. And a way to look at this is to think about what we have here is this force is 0 when psi is equal 0. This force is just linear in psi. And so we can draw a graph of what force looks like as a function of psi. So it's 0 when psi equals 0 because that's equilibrium, and then it's just linear. And so this whole thing is just a triangle. It's here. So we want the force times the distance, just the area of this. And so this is the work. And so we can just write that this is basically a half, so we're taking a triangle, times psi times the force. So we take psi, any given psi, say this value here, times the force, and then divided by 2 gives us the work done. And so we just write that the work done, which is the change in potential energy, is just minus the half because it's the triangle, and then it's the force times, so distance times the force, and then integrated over the whole volume of the plasma. And this actually integrated over, so it's the plasma plus whatever's surrounding it, so plus in this case the vacuum. And so in general we have what we have is a plasma in the middle. So here we have plasma. Then we have a vacuum region around the plasma. And then we have a wall outside. And typically what's done is we set psi equals 0 at the wall and outside the wall. So we only consider what's in the plasma and in the vacuum. And this, if you include the vacuum, this is called the extended energy principle. So if you include this bit, this is extended. And this means that we end up with a volume integral over this system. And so we typically end up with a volume integral over the plasma, plus a volume integral over the vacuum, and then plus a surface term in the middle here. So we end up with the whole delta W is delta W from the plasma plus delta W from the vacuum plus the surface integral term. So this is the surface, which is the surface of the plasma where it meets the vacuum. So there are several standard ways of writing this equation. You'll see in textbooks such as Freiberg's ideal MHD, there's a few derivations of it. If you essentially put in the force from the normal mode operator, you can do this calculation. It just takes quite a long time. I'll show you the result here. So this is the intuitive form of delta W. So you end up with the plasma term is this. So this is the plasma contribution, and there are these 5 terms. So what you can see is that these first 3 terms are all positive, so all modulus squared of something. So these are all positive, and if delta P is positive, that means that we need to put energy into the plasma to move it, and so it's at the bottom of a hill and it's stable. So these are all stabilizing terms. So this first one is the perturbed magnetic field. So this delta P perp is essentially the perpendicular component of the perturbed magnetic field, and this is the energy we're putting into the B fields. This is the Schiaffing part. So it's energy in the perturbed magnetic field, often called the field line bending term. Because what it's doing is it's taking straight magnetic field and then bending it by giving perturbation. So we start with some kind of a magnetic field like this, and then this is the perturbed part, so it's the perpendicular bit. So we give some kind of perturbed magnetic field, which essentially produces a bending of the field lines, corresponding to a Schiaffing wave. We can write down what delta B is here. So delta B perp Okay, the next part has a B naught squared over 2 mu naught, so 2 outside. So that's the magnetic pressure. And see, this is the compression in the perpendicular direction, so perpendicular to the fields. This is the curvature kappa, and this is in total this is a compression of the magnetic fields, which you can tell just from the magnetic pressure being here. These are all positive, so these are all bigger than 0. And this is magnetic compression. This part here is also stabilizing, so also bigger than 0. This is the compression. You see here, this is the adiabatic constant, and this is the plasma fluid pressure, and so this is the fluid compression. So we're doing work to squash, to compress the plasma, and that takes energy to do, and so these are all stabilizing, either compressing magnetic fields or compressing the fluid plasma. These last two terms, these are what can drive instabilities. So these can be positive or negative. This first term here is the pressure drive. So here we have the pressure and the curvature. It's called the pressure drive or ballooning drive sometimes. And the second term here, which also can be positive or negative, is driven by parallel current. This is called the kink drive. So this formula is useful because it shows reasonably clearly all the different effects. So what can stabilize the plasma and what can drive instabilities. And particularly things like the pressure gradients and the curvature interact to give stability or instability, and large parallel currents can also drive instabilities. There are a few interesting things about this. So here, for example, the compression, this is the only place where the parallel displacement comes in, because this is the compression of so divergence of the total displacement, whereas everywhere else only depends on the perpendicular components. And so what can typically happen is that the plasma can find a configuration or a perturbation where the parallel components mean that this is 0. And so typically the plasma is incompressible. So as it's compressed, the parallel flows develop so that they move out of the way, move the plasma out of the way, and so it's not compressed. So typically the plasma is incompressible because you can minimize this term. Then these terms put essentially bending of field lines is energetically unfavorable, and so what an unstable configuration will tend to do is that perturbations will be aligned to the magnetic field, and so the whole magnetic field will move in one direction rather than bending or twisting. And so there's kind of very elongated structures which are constant or nearly constant along magnetic fields, and which avoid compressing the plasma, tend to be the most unstable. And from the pressure, which we'll look at in the next few lectures, you can see that the sign on the direction of these gradients makes a big difference. And this leads on to concepts of good and bad curvature. So we can make this go unstable. If we make this negative, then this will drive instabilities. And this can be negative. Well, it's negative if these two are positive. And if these two are positive, then grad P naught and kappa must be in the same direction. If grad P naught dot kappa is bigger than 0. So in that case, they're in the same direction, and so these two will be positive. And this happens when you have a curved magnetic field. So this is B like this, and then kappa is towards the middle of the curve. So there's kappa. And if you have a pressure gradient like this, so if you have high pressure being confined by a curved magnetic field in this way, then this is unstable. And so-called bad curvature. And conversely, if you reverse the sign, so if you have high pressure on top and low pressure underneath, then this is good curvature and the system is stable. And so we'll see in the next few lectures how this works for pressure-driven modes. So the other components of delta W, so you have this is the plasma component. We then have the vacuum component, which is very similar, except we only have basically the magnetic field components. This part here actually involves the currents in the plasma. So when we work out the pressure in the magnetic field pressure, this involves currents, and so when we go into a vacuum there are no currents, and so this component goes to zero. So there's no pressure, that goes zero, and so all the components of this go to zero except this first part. And so the vacuum contribution, which is just delta W, and so it's just the total energy in the perturbed magnetic field. And so this is the vacuum magnetic field energy. And then lastly we have a term coming from the surface. So when we integrate over the volume, we end up with a surface contribution. So we'll try and understand this a bit better in future videos, but this essentially can be made to go to zero if the plasma is smooth towards the boundary. We show that this basically involves a jump in the gradients at the boundaries, so a surface current. So it's like basically driven by surface current. So if the plasma solution is smooth, then this term can be made to go to zero. But there are some modes, so peeling modes for example, which can be driven by these surface contributions.